All right, welcome to the deep dive. You know, I think you know why you're here, right? I think you're here because you want to get smart fast and about what really matters, but you don't want to be totally bogged down by like details and information overload.
Absolutely.
Today, we're going to be looking into something that is like super groundbreaking in AI. I mean, this is pretty cutting edge stuff. It's a new way for robots, even like self-driving cars, to really to get a better grasp, a deeper understanding of the world around them, and to do so in a much safer way than what we've seen before.
Yeah, I mean, we're talking like a fundamental shift in how, physical AI, the
hmm
kind that like actually moves around and interacts with the real world, how it's going to be learning and operating.
I like that, physical AI.
It's giving these systems, more of a like an intuitive grasp, I guess, of physics and how things work.
So that's a great place to start, right? I mean, we've all seen AI do really incredible things in the last few years, like understanding language or even recognizing images. But when we're talking about physical AI, the kind that has to actually move around in the world, that's where things get really tricky. And it seems like a lot of that comes down to the training process and the data or the lack of data that these systems have access to. What's the main hurdle there?
Well, the problem is, I think, as you alluded to, is data. It's all about the data.
hmm
Think about like a robot learning to pick up, you know, different types of objects, right? In the real world, every single time that robot fails to pick something up that's a dropped item, that could be a broken item. I mean, think about a self-driving car. Every mistake it makes in the learning process, I mean, the repercussions there could be pretty huge. So you're right, the challenge is scaling up that learning process and making it safe and efficient in the real world. It's really, really hard to do.
Yeah, there's a lot at stake. So it seems like this new concept of a World Foundation model, a WFEFM, is trying to address that exact challenge. It's essentially like creating a digital twin of the real world, right? This virtual space where AI systems can practice and experiment without actually breaking things or causing any kind of real world harm.
You got it. That's precisely what we're talking about, like a sophisticated digital copy of reality, right? A virtual playground for these systems to mess around in and learn, all without any real-world consequences.
It makes sense. So, for today's deep dive, we're really going to be focusing on this new platform, Cosmos. And that's COSMOS. And it's a platform that's built upon this idea of World Foundation models. And what we really want to understand is, what is Cosmos? Like, what does it offer to the world of physical AI? And why should we be paying attention to it? Why is this potentially such a big deal?
Yeah, great questions. Let's dive in.
Okay, so let's start with the basics here. Let's define what exactly we mean by physical AI. It might seem pretty straightforward, but let's make sure we're all on the same page.
Yeah, sure. So when we say physical AI, we're talking about AI that has a physical presence in the world. It's not just software running on a computer somewhere. It's embodied in some way. And to be embodied, it needs two key things. First, it needs sensors, things like cameras, LiDAR, maybe even tactile sensors, to feel things, to perceive its environment. It needs to be able to see or feel what's around it. And second, it needs actuators, like motors or robotic arms or wheels, something that allows it to actually act on that environment. So if it can both see and do things in the real world, then we're talking about physical AI.
So, if it can both sense and act in the world, it's physical AI. That makes sense. But the real potential here, I mean, that's where things get really exciting, right? Because we're talking about a world where we could have robots doing really dangerous jobs, things that we don't want humans to be exposed to, maybe working in hazardous environments or helping to build complex products, stuff that requires a lot of precision. We could even see robots doing more mundane tasks like managing logistics in warehouses.
Absolutely. That's exactly right. We could have AI systems helping us with everyday tasks, providing care, even just doing the chores that nobody wants to do. I mean, self-driving cars are a great example. If we can get the technology right, that's a massive change in how we all live and move around. So the potential here is, it's really huge. It could touch almost every part of our lives.
But we keep coming back to this issue of training. It's not just about building the robots or the cars. It's about teaching them how to operate in the real world safely and effectively. And as we've said, that's where the challenge of data really comes in. Can you walk us through that? What's so difficult about getting enough training data for physical AI systems?
It's all about the type of data they need. For a physical AI to actually understand the world, to know how to move and act within it, it needs to learn from like specific sequences of events. It needs to see what happens when it takes a certain action, like if a robot arm moves a certain way. It needs to understand the consequences of that movement. So what it needs is observations from its sensors, like what it sees or feels, paired with the actions it took, and the outcome of those actions.
So they need this constant feedback loop, this cause and effect data, to learn how to interact with the world.
Exactly. And that's where the challenge comes in. Because if you think about it, how do you get that data in the real world? You'd have to let the AI just run around, bumping into things, making mistakes to learn from its actions. And as we've discussed, that's not really practical. I mean,
Yeah.
think about the potential for damage, the cost, the time it would take. That's where world foundation models come in. It's about creating a safe space where they can learn and make mistakes without any real-world consequences.
So that's the idea behind Cosmos, right? It provides these WFMs, these digital twins of the world, where you can train these systems without all the risk and cost of doing it in the real world. It's kind of like a simulator, I guess. But I imagine these are pretty sophisticated simulators.
Yeah, way more advanced than the simulators you might think of for like video games or flight training. We're talking about models that have been trained on massive amounts of data, real-world data, to understand the physics and nuances of how things actually work.
So it's not just one WFM, it's a whole collection, a suite of these pre-trained models that developers can access.
Exactly. And what's really interesting is they've actually included different types of WFMs within Cosmos. They have what are called diffusion models and autoregressive transformer models. So it's not just one approach. They're exploring multiple ways to model the world, which I think is really smart.
Diffusion and autoregressive. I know I've heard those terms before, but I think it was in the context of generating images. How do those concepts apply to modeling the world within Cosmos?
You're right. Those techniques have been really successful for image generation. And now they're being applied to video and even to understanding the physical world. The key difference between diffusion and autoregressive models is how they represent and process video data. Think of a video as a sequence of images, right? Diffusion models in Cosmos work with what we call continuous latent representations of those images. Imagine a fluid, unbroken flow of information that captures the essence of the video. Autoregressive models, on the other hand, use discrete latent representations. It's more like breaking the video down into a sequence of distinct digital tokens that represent specific elements or moments within the video.
So it's like one is seeing the world as a smooth, continuous stream, while the other is more like a series of snapshots or, like you said, tokens that capture specific pieces of information.
Exactly. And that difference stems from the ways they're trained. But what's important is both of these types of models in Cosmos are trained to be generalists. They've been fed huge data sets of video, diverse data sets that show them a wide range of real-world physics in action. So they come preloaded with a pretty solid understanding of how the world works.
They have a basic education, so to speak. But how do you then take one of these models and actually apply it to a specific task? Let's say you're building a robot arm to work on a specific assembly line. You're not going to use a general world model for that, right?
Right. That's where post-training comes in. Think of the pre-trained WFM as having this broad general knowledge. To make it useful for a particular task, you need to give it some specialized training. That's what post-training is all about. You give the model smaller, more focused data sets that are tailored to the specific task or environment that your physical AI will be operating in.
So it's like taking someone with a good general education and then sending them to trade school to learn a specific skill. Makes sense. What does that post-training data look like?
Usually it involves pairs of prompts and corresponding videos. So the prompt might be something like a command or an instruction. For that robot arm, it could be something like place the blue gear on the spindle, or it could be a more general instruction. If we're talking about a self-driving car, it might be a specific route to follow. And then the corresponding video shows the correct execution of that prompt, whether that's captured in the real world or from a really accurate simulation. And because the WFL already has a pretty good understanding of the world, this post-training data set doesn't have to be nearly as large as if you were starting from scratch.
I see. You're leveraging all the work that went into building that initial foundation. You're basically saying, okay, you know the basics, now let's teach you the specifics of this particular job.
Exactly. It makes the process way more efficient.
Yeah.
And that's a big part of why Cosmos is so exciting. It provides both the foundation and the tools to then specialize that foundation for all sorts of different applications.
Now, I know you mentioned that the quality of the data used to train these WFMs is absolutely crucial. How do they actually go about building those massive data sets? It must have been a pretty massive undertaking.
Yeah, data curation was a huge part of the project. They built a pretty sophisticated video data pipeline to handle it. The goal was to sift through mountains of raw video footage and find the segments that were actually valuable for training these models. So it wasn't just a matter of grabbing any video they could find, it was about being really selective.
So not just dumping random YouTube videos into the system, it had to be more thoughtful than that. What was their starting point?
They began with a ridiculous amount of raw video. We're talking like 20 million hours.
Mm.
And the resolutions range from, decent quality like 720p all the way up to 4K. But even with that much footage, they knew that a lot of it wouldn't be very helpful. There would be a lot of redundancy, videos that didn't really show much in terms of motion or dynamics. So they built this pipeline to refine the data, to really pull out the good stuff.
What did that pipeline involve? How did they go from raw footage to something that was actually useful for training these models?
Well, it was a multi-step process. They started by splitting those super long videos into shorter, more manageable clips. Then they filtered out all the irrelevant stuff, things that weren't really showing dynamic motion or that were just, low quality. They also added annotations to the videos to help the AI understand what it was seeing, and they had to deduplicate to get rid of any repeats in the data set. And finally, all of that processed data had to be organized and prepared for training.
I'm curious about the splitting part. I mean, how do you even decide where to make the cuts in a video? Is it just arbitrary?
No, not at all.
Hmm.
They looked into a bunch of different algorithms for detecting shot boundaries, places where one continuous camera shot ends and a new one begins. They found that neural networks, specifically one called Transnet V2, did a really good job, especially for videos with lots of edits and complex transitions. They actually created their own benchmark data set, which they called Shot Bench, just to evaluate how well these different algorithms performed.
So they were really rigorous about making sure they're getting clean, distinct clips. What about filtering? What kind of things were they trying to get rid of?
They did a few different types of filtering.
Yeah.
One was motion filtering, which is basically looking for videos that are either completely still or that have really shaky, erratic camera movement. For that, they used a classifier that was trained on optical flow data.
Mm-hmm.
That data basically shows how things are moving within the video. If it's too static or too chaotic, it gets filtered out.
Mm-hmm.
They also tagged videos with different types of camera motion, like panning, zooming, tilting, things like that. That could be useful information for the AI to have during training.
Yeah, that makes sense. And I'm guessing that not all video content is equally valuable when it comes to learning the laws of physics, like a video game versus a nature documentary.
You got it. They did what's called video type filtering to control the mix of content in the dataset. They had a classifier that could identify different types of videos, like, whether it was a documentary, an action movie, animation, things like that. And then they could intentionally adjust the balance. So they could exclude things like video game footage or animation, because that doesn't really reflect real-world physics.
Hmm.
And they could oversample things that were really relevant, like videos of people interacting with objects or performing actions. It was all about being very intentional about the type of data they were using to train the models.
So it was a very carefully curated data set. And I know they actually used a visual language model to add captions to the video clips. That seems like a pretty important step in helping the AI make sense of what it's seeing.
For every 256 frames, they automatically generated a caption using a really good visual language model. It's like adding a little bit of extra information, like a label, to help the WFM connect the dots between the visual information and the meaning behind it. And to top it all off, they built a visual search engine on top of all this curated data. So they could search through millions of videos using text descriptions or even using other videos as examples. It was a really cool way to explore the data set and debug any problems they were having.
It sounds like they really thought of everything. They've got this mountain of data carefully selected and processed. They've got all these annotations and captions, and then they have to organize it all in a way that can be efficiently used to train these massive models.
Exactly. And because they're dealing with such a massive amount of data, they had to build a pretty sophisticated infrastructure to handle it all. They use something called AnyScale Array, which allows them to distribute the workload across tons of different computers. That way they can take advantage of all the available computing power and process everything in parallel.
So now we've got the data piece figured out, but how do they actually go from this video data to a working WFM? You mentioned video tokenization earlier. What's the point of that?
Video tokenization is all about finding a more efficient way to represent those videos. Think of it like compressing a video file, but instead of making it smaller for storage, you're transforming it into a format that the AI models can understand and process more easily.
So it's about finding the essence of the video, the key information that the model needs, and getting rid of all the extraneous stuff.
Yeah, something like that.
Yeah.
Video files contain a ton of data, and training these big, complex WFMs takes a lot of computing power and memory. So you need a way to simplify things. And the idea is if you can convert those videos into a sequence of tokens, each token representing a specific element or feature of the video, then you can make the training process much more efficient.
And they built their own system for this. the Cosmos tokenizer.
Yeah, they did.
Yeah.
And they used a pretty clever design. It's what's called an attention-based encoder-decoder architecture. Basically, it learns how to effectively turn a video into a sequence of tokens and then back again. And what's really interesting is that it's what's called a causal tokenizer. That means when it's looking at a frame in the video, it doesn't consider any information from frames that come later in the sequence. It only looks at the past and present.
I'm curious why that matters. Why build it that way?
Well, it has a couple of big advantages. For one, it allows them to train the models on both images and videos at the same time, which is a really clever trick. Because if you think about it, an image is just a video with only one frame, right? So by using a causal tokenizer, they can feed the model images alongside videos, and it can learn from both without getting confused. That lets them take advantage of all the huge image data sets that are already out there. And another advantage is that it aligns better with how real-world physical AI systems work. Those systems make decisions based on what they've observed up to that point, not on what might happen in the future. So a causal tokenizer is a more realistic representation of how those systems operate.
That makes sense. And this Cosmos tokenizer, how does it compare to other approaches out there?
Well, they tested it on a bunch of standard benchmark datasets and found that it actually outperformed other existing methods by quite a bit. It was better at capturing the important information in the videos, so when you convert back from tokens to video, you get a higher quality reconstruction. And it was also faster, which is always good. They even made their pre-trained tokenizers publicly available so other researchers can use them for their own projects.
Cool. So they've got the massive high-quality data. They have a really efficient way to represent that data as tokens. Now we can finally get to the actual world foundation models. We've talked about these two types, diffusion-based and autoregressive. Can you break down how each of those approaches works within Cosmos?
Sure. So the diffusion models, they work in kind of a backwards way. Imagine you take a video and you gradually add more and more noise to it until it's just this blurry mess. That's what the diffusion process is all about. And the diffusion model learns how to reverse that process. So to create a new video, you start with random noise, and then the model gradually denoises it step by step, guided by whatever prompt you give it. That prompt could be a text description of what you want to see, or it could be an initial frame or sequence of frames to build on. They've got a couple of different diffusion models in Cosmos. Text-to-world models can generate future video based on a text description, and video-to-world models can predict what's going to happen next in a video, optionally guided by some text. And these diffusion models use the continuous tokens that we talked about earlier.
So it's like taking a blurry image and slowly bringing it into focus. It starts with chaos and then refines it into something coherent. That's pretty neat. What about the autoregressive models? How do they approach the problem?
Autoregressive models are more about prediction. They look at what's happened in the past, and then they predict what's going to happen next. So in Cosmos, they've got autoregressive models that are specifically trained to predict the next frame in a video sequence, given the frames that came before. And they even have versions that can take text prompts into account. So you can give the model some text, like a description of what you want to happen, and the model will try to incorporate that into the video it generates. And these models use the discrete tokens that we talked about.
So they're building the video step by step, like writing a story, and they can even take suggestions from the user about what should happen in the story. That's pretty cool.
Yeah, and both of these approaches have their own advantages and disadvantages. But the Cosmos team has done a lot of really clever engineering to make both of these types of models as efficient as possible. They've come up with ways to reduce the number of parameters in the models, which makes them faster to train and run. And they've also explored different ways to parallelize the training process so they can distribute the workload across multiple GPUs and make it all run much faster. It's a really impressive feat of engineering.
It sounds like they've put a ton of work into just getting these models up and running, but the real test is how well they perform in real-world applications. How do you actually go from these pre-trained Cosmos models to something that can solve a real problem?
That's where post-training really shines.
Yeah.
They actually showed a few examples in the paper of how they've fine-tuned these models for different tasks. And the results are pretty impressive.
What were some of the applications they highlighted?
One really interesting example is in the area of camera control. They were able to train at WFM to generate these really realistic navigable virtual worlds. You could give the model a text description, maybe a starting image, and some camera parameters, and it would create a video that felt like you were moving around in a real 3D environment. They even used a mathematical technique called plucker embeddings to represent the camera's position and orientation really precisely, which made the control much smoother and more realistic.
So you could tell the AI something like, show me this room from over there, and it could actually generate a video that looked like you were physically moving the camera? It's pretty wild.
It is. And it has all sorts of potential applications. Think about virtual reality, or maybe even training robots to understand how to navigate their environment. It's really powerful stuff. Another cool example was in robotic manipulation. They trained WFMs to understand action commands and then to actually control robots to perform those actions.
Yeah.
They showed that these models were able to pick up objects and move them around based on instructions, and they actually outperformed other models that didn't use this WFM approach.
So you could potentially have robots in a factory that can understand and respond to human instructions. That would be a game changer.
Absolutely.
Yeah.
And it could make robots a lot more flexible and adaptable. Instead of having to program them for every specific task, you could just give them high-level instructions and they could figure out how to carry them out. The third big example they showed was in the area of autonomous driving. They had access to this huge internal data set of real-world driving data captured from multiple camera angles, and they used that to train these multi-view world models. Basically, the models can predict what's going to happen next in a driving scene from different perspectives. And they show that these models were really good at generating realistic and consistent driving scenarios.
So you could have a self-driving car that can not only see what's around it, but that can also anticipate what other cars are going to do and plan its own movements accordingly.
Exactly. And that's crucial for safety. If a self-driving car can predict what's going to happen, it can make better decisions to avoid accidents. So these world models could be a really important step towards making autonomous vehicles more reliable and safer.
Now, all of this sounds incredibly powerful, but with any powerful technology, there's always the question of responsible use. What kind of safeguards are built into Cosmos to prevent misuse? We don't want people generating harmful content or using these models for malicious purposes.
Right. And they've thought about that. They have a pretty comprehensive system in place. It's a two-stage system that they call pre-guard and post-guard. The pre-guard system is designed to catch any potentially harmful prompts before any video generation even starts. So they have a list of keywords that are automatically blocked. And they're also using a more sophisticated system that's based on a large language model. This LLM can understand the intent behind the prompt and identify things that might be dangerous, like prompts that are related to violence or hate speech.
So it's like a safety net that catches the bad stuff before it even gets processed.
Yeah. But even if something slips through that first layer of defense, they also have the post-guard system. This system analyzes the generated video content itself, and if it detects anything harmful, it can block the video from being outputted. They've got a video content safety classifier that can recognize things that are unsafe, and they also have a face blurring filter that can automatically blur out any faces that appear in the video. That helps to protect people's privacy and prevent misuse.
They've clearly thought this through. And I know they also had a red team that was specifically tasked with trying to break the system, right, to find any weaknesses in these safeguards.
Exactly. The red team's job is to think like an attacker. They try to come up with all sorts of creative ways to trick the system, to try to get it to generate something harmful, and then they carefully analyze the results and they use that information to improve the safeguards. So it's an ongoing process, but they're definitely taking it seriously.
That's good to hear. So as we wrap up here, can you put this into context for us? How does Cosmos relate to other research that's happening in the field of world models and video tokenization? Where do you see this kind of technology going in the future?
The idea of world models has been around for a while, especially in robotics and control systems. But the recent advances in AI, particularly in generative AI, have really opened up new possibilities. Cosmos is building on those advances, pushing the boundaries of what's possible. They're using really powerful models and very efficient methods to train these world models directly from video data. And I think that's a really promising direction. A lot of earlier world model systems relied on simpler models, but Cosmos is really taking advantage of the latest breakthroughs.
And where do you see this all going in the next few years?
Well, there are a lot of exciting possibilities. One thing that people are really interested in is combining these visual world models with the knowledge contained within large language models. So imagine a world model that not only understands what it sees, but that can also reason about the world, understand concepts, answer questions, things like that. That would be a huge step forward. And another area that's really interesting is looking at hybrid approaches, combining diffusion and autoregressive models to get the best of both worlds. That could lead to even faster and more efficient video generation with higher levels of realism. And of course, there's a lot of work to be done on the evaluation side. How do you actually measure how good a world model is? There are no easy answers there, so researchers are coming up with new ways to evaluate these models, both automatically and through more controlled experiments. So it's a really exciting time to be working in this area. There's a lot of potential for breakthroughs in the coming years.
Absolutely. It seems like we're just scratching the surface of what's possible. This has been a fascinating deep dive into Cosmos. It seems like a really significant step forward in the field of physical AI, with the potential to impact so many different areas of our lives.
Agreed. It's definitely something to keep an eye on.
Well, thanks again for taking us on this journey. It's been incredibly informative. And for our listeners out there, thanks for tuning in to the deep dive. We'll see you next time.
Thank you for listening and stay tuned.